Hello everyone and welcome to today's webinar. For those of you joining us for the first time, please note that audio is provided via the GoToWebinar app over the internet. So please enable your speaker in all places. The application has already muted your microphone. That being said, you can still ask me questions during the webinar. There is a questions tool on the right side of your screen. You can use this mechanism to type in any question you have at any time. I will either read the questions during the webinar and answer them, or I will send you a document full of all the questions and answers sometime this week. Today we're going to talk about calculating unit mean time to fail spurious within exSILentia. But first, I'd like to introduce myself. My name is Kate Hildenbrandt. I'm a product sales engineer here at exida. I previously spent 7 years in the gases and chemicals industry doing project work and plant process engineering as well as process safety. However, my role at exida is to ensure customer success by providing training and application support for users of our tools. So anything you want to know about what the tool does, how to do it, I can help with that. A little overview on exida. exida is a leader in functional safety tools, consulting, and assessments. We are an ANSI accredited certification body for functional safety and cybersecurity. We have many active members on the functional safety committees, and we have locations internationally. So here you can see all the locations we have around the world. I am located in Sellersville, Pennsylvania, which is a little bit outside of Philadelphia, but hopefully on this map you can find somebody who is located close to you that works for exida. So today we're going to talk about safe failures. What is a safe failure? How do you calculate the mean time to fail spurious for a SIF and then for a unit? I'm going to do both of these calculations quote unquote by hand, and then I'll show you how you can do them in exSILentia. First, I'm going to go through a few definitions. What is a safe failure? So often in safety we focus on dangerous failures, and this is very understandable because a dangerous failure could harm personnel, equipment, and the environment. So what is a dangerous failure specifically? It's a failure that prevents a device from responding to a potential dangerous condition or hazard scenario. We often symbolize a dangerous failure rate using lambda D. However, safe failures are pretty important too. A safe failure is defined as a failure that causes a device to go to the safe state. This is going to trip your plant most likely, and as a result, you have loss of production for some sort of downtime. A safe failure rate is often symbolized using lambda S. So let's give an example of these two. In this example, we have a furnace with a main fuel inlet line. On this inlet line, we have a valve that stays open during normal operation. However, if there is a hazard scenario, to achieve the safe state, that valve is going to close, it's going to halt flow of fuel into the furnace, and everything should be safe. However, what if there is a failure? A stuck stem is a good example of a dangerous failure in this scenario. In this case, the valve cannot close, and the fuel is going to continue to flow into the furnace. At this point, an incident is possible as the safe state cannot be achieved. And for a furnace, you might have a furnace explosion. On the other hand, you could have a safe failure. An example of this would be an actuator leak. You would lose instrument air pressure in this case, and the spring would force the valve closed during normal operation. This is going to halt production, and you're going to have some period of time where the plant is down. Obviously, this is going to hurt production of the plant, and therefore it's going to be an expense. So there is your example of a safe failure. Well, why is the safe failure rate important? Well, as I said, functional safety standards often focus on the dangerous failure rate due to the potential harm to personnel, equipment, and the environment. This is of the utmost importance. But for an operating company, The ability to produce is a very close second priority. Interruptions in production can be very costly, which emphasizes the need to minimize spurious trips. So how do we quantify this? We have the spurious trip rate. The spurious trip rate is defined as the frequency at which a device, a SIF, or an entire unit needlessly transitions to the safe state, without a demand from the system. So anytime your plant trips due to a failure of a device, SIF, or unit. For a single device, the STR is equal to the safe failure rate. That's our lambda S. And like the failure rate, STR is typically expressed in failures per hour, so this is a frequency. The STR is a useful metric, expressing the equivalent safe failure rate for more complex configurations, if you have redundancy in a SIF, or if you're evaluating a complete unit. So you would want to calculate the STR and minimize the frequency of your safe failures. Here I'm showing you some simplified formulas for the STR, and hopefully they make some sense. In a 1 out of 1 configuration, again, you're just dealing with that one device, and so the spurious trip rate would be equal to your safe failure rate. In a 1 out of 2 configuration, let's say you have 2 valves in series, you are twice as likely to have a spurious trip because you have those 2 valves. So in this case, the spurious trip rate is 2 times the safe failure rate. Then we get into more complicated configurations, for instance, the 2 out of 2 and 2 out of 3 configurations. Let's take 2 out of 2, for example. In this case, if you have 2 valves in parallel, both of them are going to have a safe failure to trip the plant. And therefore, you have the safe failure rate squared in the numerator of that equation. It's a complicated equation. The capital T is symbolizing the proof test interval of that configuration. So these are simplified equations, and they're pretty simple. They are derived from Markov models, but you would really use them to understand how redundancy is going to help minimize your spurious trip rate. So let's take a look at that. If I assume a safe failure of 5 times 10 to the negative 7 per hour and a test interval of 1 year, or 8,760 hours, I can calculate a spurious trip rate for these scenarios. So again, in a 1 out of 1 configuration, your spurious trip rate is going to equal your safe failure rate. So that's going to be 5 times 10 to the negative 7 trips per hour. For a 1 out of 2 configuration, you're simply multiplying that by 2, as we said earlier. However, you'll notice a dramatic decrease in the spurious trip rate in the 2 out of 2 and 2 out of 3 configurations. In this case, the 2 out of 2 is the lowest value for the spurious trip rate, and therefore that is what you would want to pick to optimize your configuration to minimize your spurious trips. So that is a pretty good overview of the spurious trip rate, but there's another metric to consider. Some people like to talk in terms of mean time to fail spuriously. This is defined as the average time until a device, SIF, or unit has a safe failure. It is typically expressed in years. The MTTFS is simply the inverse of the spurious trip rate, and many prefer to use this to the STR since it is easier to relate to a time interval than a rate. So unlike the spurious trip rate, which we want to decrease, we want to increase the amount of years it takes between spurious trips. So let's give a little more context to this metric. The MTTFS is not a guaranteed time between safe failures. It is an average. As an example, if the MTTFS is 1 year, it is possible that you would have 2 false trips in the first year and 0 in the second. This would still result in an average of 1 year. So as you can see, it is not a guarantee. We cannot say because the MTTFS is 1 year that we're guaranteed to have no trips within that first year. Likewise, if the MTTFS of a pressure transmitter, let's say, is 50 years, and you have 50 pressure transmitters of that kind in your system, it is possible to have one false trip per year. So again, this is an average, it's not a guarantee, but it remains a useful metric that many strive to maximize in order to increase uptime in their system. So now that we know how valuable these calculations are, let's look into how we would calculate the MTTFS for a SIF. I have a simple SIF here. In this case, you have 3 sensors, which are pressure transmitters, in a 2 out of 3 configuration, sending a signal to the logic solver, which then controls 2 final elements in a 1 out of 2 configuration. In this case, we're going to assume that the pressure transmitters are identical, each with the safe failure rate of lambda SS. Likewise, let's assume that the 2 final elements are identical, each with a failure rate of lambda SFE. And going along with that nomenclature, let's assume that the safe failure rate of the logic solver is lambda SLS. In this case, the STR of the SIF is equal to the sum of the STR of each part of the SIF. So the STR of the sensor group in a 2 out of 3 configuration is that same simplified equation that we saw earlier. And you can see that in the first part of the equation using lambda SS. And then the STR of the logic solver is simply the safe failure rate of that logic solver. Finally, for the final elements, you have the STR equaling 2 times the safe failure rate of that 1 out of 2 configuration. So we use the simplified equations from before to come up with this total STR of the SIF. Now, if we'd like to calculate the MTTFS instead, you would simply take the inverse of that STR equation. I do have a quick warning here that you want to watch your units. As I said, the STR is typically expressed in failures per hour, but the MTTFS is typically expressed in years. The way I've calculated it here, the MTTFS is expressed in hours, and therefore to convert to years, you have to divide by 8,760 hours. So if you're doing this by hand, you want to make sure to watch your units, but hopefully you don't have to do it by hand. I'm going to show you next how you would calculate the MTTFS with a tool like exSILentia. In this case, we're using our SIL verification module, which we call Silver. I have a few notes on Silver before we get to the calculation. exSILentia uses a discrete time-based Markov model calculation instead of the simplified equations that I showed you before. And this helps to determine a very accurate STR value for the devices, the SIFs, and the units. So here's an example Markov model. Again, those simplified equations were derived from a Markov model, and so exSILentia is using that technique to make sure that you have precise calculations for any type of architecture. Additionally, exSILentia will provide you with the safe failure rates you need. So we have what we call the Safety Equipment Reliability Handbook, which provides relevant failure data for thousands of devices used industry-wide. All you have to do is select your equipment in the tool, and every type of failure rate is provided. Now, this is a little bit rare. Sometimes manufacturers don't give out the safe failure rates of their devices. Again, people like to focus on those dangerous failure rates. But we now see the value of the safe failure rate, and if you're using exSILentia, you're going to have that information at your fingertips. So again, once you select that equipment, exSILentia is going to calculate for you your achieved SIL level, your PFD average, and your mean time to fail spurious. Here I have a screenshot of a few final elements, and you can see that the equipment is chosen from a drop-down menu, from the STRH. Then you're going to model your SIF. So here you can see how a SIF is modeled in exSILentia. I have my 3 pressure transmitters in a 2 out of 3 configuration, which send a signal to my 1 logic solver. That logic solver is then going to control my shutdown valves, which are in a 1 out of 2 configuration. And below that, you can see all of the results. exSILentia will output the MTTFS for the sensor group, the logic solver group, and the final element group. And then it will also output the complete SIF MTTFS. In this case, that is 52.36 years. So again, to keep this in context, if you have 52 of these SIFs completely independent, you might have 1 failure per year. But what you can do in exSILentia is you can model your SIF. You can see the mean time to fail spurious, and you can say, I want this to be 100 years instead of 50. And you can make different selections, equipment selections, and different SIF architectures to optimize your system to make sure that you have a minimum level of spurious trips. So that is calculating it for a SIF. But what if we want to calculate it for a unit? The unit's a little bit more complicated. So I'm going to attempt to do this by hand, but you're going to see that I'm not entirely successful. First, let's look at the example. This is a furnace unit. Again, we have a main fuel line into the furnace. This has a few final elements on it, XV101, which is in a 1 out of 1 configuration, and then XV301 through 304, which are in a 4 out of 4 configuration. We have 3 pressure transmitters on the main fuel line in a 2 out of 3 configuration. And we also have an instrument air line going into each of the final elements, which has a pressure transmitter PT201 in a 1 out of 1 configuration. Finally, we have 4 flame scanners inside the furnace looking for loss of flame. They are in a 2 out of 4 configuration. So, taking this example into account, we want to consider a few potentially dangerous scenarios. So, what if you have high pressure in the fuel supply line? In that case, you might have too much fuel in the furnace, which could cause an explosion in that furnace. So we have a SIF to protect against that. What if you have low instrument air pressure in the instrument air line? In this case, you're not controlling your valves optimally, and therefore you could have a little bit too much fuel or a little bit too little fuel in the furnace. Again, this could cause a potential hazard, such as a furnace explosion. And finally, what if there is loss of flame in your furnace? If your fuel is not being burned off, you might gather too much fuel in that furnace. And once the flame comes back, you might have a furnace explosion. So we're going to take a look at all 3 of these scenarios and the SIFs that protect against them. And we're going to try and calculate our spurious trip rate and our mean time to fail spuriously. So for the first SIF, this is our high fuel supply pressure SIF. You have, again, 3 pressure transmitters in a 2 out of 3 configuration going to the logic solver, which is controlling the 5 final elements. For XV101, you have a 1 out of 1 configuration, and for the other 4, you have a 4 out of 4 configuration. And we know the simplified equations for some parts of the SIF. So for the sensor group, again, it's 2 out of 3, so we have that simplified equation for the STR, which you can see there. In this case, the safe failure rate is symbolized by lambda SS1. For the logic solver, you have a 1 out of 1 configuration, so the STR is equal to the safe failure rate of that logic solver. In this case, I'm assuming that the safe failure rate of this logic solver is the same for all 3 SIFs and for the unit. In a little bit, we're going to see that that's not necessarily true, but for the sake of simplicity, let's assume that the logic solver always has that STR of lambda SLS. For XV101, we have a 1 out of 1 configuration. So again, the STR is equal to the safe failure rate, which is lambda SFE in this scenario. But these last 4 final elements in a 4 out of 4 configuration, we do not have a simplified equation for. It's a little bit too complicated. So instead of having the STR equation, I'm simply going to put in STR FE 4 out of 4. So at the bottom you see the equation for SIF1. STR SIF1 is equal to the STR of each component, which you can see there. Well, what about SIF2? Well, in this case, the only thing that's different is the sensor group. So PT201 in a 1 out of 1 configuration has an STR of its safe failure rate, which is lambda SS2. However, everything else in this SIF is the same as last time. So the rest of the equation would be identical, and you can see the STR for SIF2 equation at the bottom. And finally, we have the loss of flame SIF. In this case, again, the only thing that's different from the other two is the sensor group. These flame scanners are in a 2 out of 4 configuration. And again, we don't have a simplified equation for the STR of that kind of configuration. We have no choice but to say that it is STR sensor group 2 out of 4. And then you would add that to the safe failure rate of the logic solver of XB101, and then the STR of FE2, 4 out of 4. So those are the 3 equations for 3 SIFs separately. But how do we calculate the STR for the entire unit? You might think you would just add up the STR of each of the individual SIFs, but this is not so. That would be a correct assumption if you have 3 completely independent SIFs. However, in this case, the logic solver and the final element are reused. So if you use the equation that way, you would triple count the logic solver and the final element groups. Instead, the STR of the unit is simply the STR of the first sensor group, the 2 out of 3 group, the second sensor group, 1 out of 1, and the third sensor group, the 2 out of 4, plus the safe failure rate of the logic solver once, the safe failure rate of XV101, and the STR of FE 4 out of 4. Again, you're only counting the STR of each component once. And so that is how you would add together the safe trip rate of the entire unit. Now, to get the MTTFS of the unit, you would have to take the inverse of that STR equation. So again, 1 over the STR of the unit would give you MTTFS of the unit. So again, I wasn't entirely successful in calculating these factors. In fact, even if I had the safe failure rates of each piece of equipment, I would not have been able to do this by hand because I didn't have the simplified equations for each configuration. So instead, I would have to turn to a tool like exSILentia. So I'm going to show you how you might calculate the MTTFS for a unit with exSILentia. And again, this would be using the silver module of the tool. The first thing we would have to do is categorize the SIFs by unit. And so in exSILentia, we would do that using the SIF identification tab. Here you can see for SIF1, I have attributed it to the unit furnace, and I did the same for the other 2 SIFs within the tool. Then you would model the SIFs. Each SIF is modeled easily in exSILentia by selecting the devices and the architecture for each group. You can see a screenshot here of sort of the overview of each SIF, and hopefully they look familiar to you by now. But you see SIF 1, SIF 2, and SIF 3. The tool allows the users to identify devices that are reused. So in this case, the logic solver and all 5 final elements are being reused. I have a small screenshot here of the burner valves, which is our 4 out of 4 configuration, and how I check the reuse this group checkbox. And the tool actually notes that this group is used 3 times, which is correct because it's used for all 3 of these SIFs. Another way to take a look at how your devices are being used is with a cause and effect matrix. This is an output of exSILentia. So if you take a look at this matrix, you'll see that each SIF is categorized by its logic solver. So you see logic box there on the lower left-hand side. And the next column is showing every single sensor that is giving a signal to that logic box. So you see your 4 flame scanners and the 4 pressure transmitters of our example. Other information in here includes the cause, the type, the range for these sensors, the limit value, and the engineering units. And then you can see how the voting works. Finally, where there's a dot in the intersection, you see which sensors help to control which final elements. And in this case, all sensors go into the logic box, which controls all final elements. You see XV101 there in its 1 out of 1 configuration, and then XV301 through 304. So this is a good high-level look at how your SIFs are operating within your safety instrumented system. You might see below that I have my sample SIF in here that we use to calculate the STR and MTTFS of a simple SIF, and that had the pressure transmitters in the 2 out of 3 configuration, and then the final elements in a 1 out of 2 configuration. You can see how the different units are separate and how the cause and effect matrix is a very helpful summary of how your SIFs are operating within your system. But finally, you would model each of the 3 SIFs in the Silver tool. So here's SIF 1. Hopefully it still looks familiar to you in the tool. You have your sensor group, which is your pressure transmitters in a 2 out of 3 configuration, sending a signal to your logic box, which controls your final elements. The main fuel valve is your XV101, and your burner valves are XV301 through 304. You could see how the main fuel valve is in a 1 out of 1 configuration, and the burner valves are in a 4 out of 4 configuration. Finally, just like with the SIF, the MTTFS for each part of the SIF is calculated, as well as the total MTTFS for the entire SIF. In this case, we want to focus a little bit more on the parts, because we're trying to calculate the MTTFS for the entire unit. So, remembering our equation when we tried to do it by hand, you want to take into account the sensor part, the logic solver part, and the final element part. Now, this would be the only time we really take a look at the logic solver and the final element, because we know that we only want to add them to the equation once. So moving on to SIF 2, you would focus on the sensor part of this SIF. Again, that's the only thing that's different. You have your pressure transmitter in a 1 out of 1 configuration, sending a signal to the logic box, which then controls the same final elements. Now you might notice that the final element, MTTFS contribution here, is the same number, but the logic solver, MTTFS, changed. So you might remember that when I tried to do this by hand, I assumed that the safe failure rate for the logic solver is consistent whether it's for SIF 1, SIF 2, SIF 3, or the entire unit. Now that is not entirely accurate, and I'm going to explain why in a minute. But first, let's look at SIF 3 in exSILentia. SIF 3 has the 4 flame scanners in a 2 out of 4 configuration. And so here I've circled the MTTFS for that sensor part. Again, the logic solver number has been changing, and so I'm going to explain why. exSILentia correctly calculates the safe failure rate for each configuration of the logic solver based on the number of inputs and type of inputs and outputs. So you can see here by the diagram that the SIF inputs are different for SIF 1, SIF 2, and SIF 3. That is going to affect your safe failure rate for the logic solver, depending on how many components there are. Also depending on the type of inputs, whether it's digital or analog. In this case, the outputs are consistent, but you could see how the safe failure rate of the logic solver is not going to be the same for SIF 1, SIF 2, SIF 3, or the entire unit. They're all different safe failure rates. This results in a different MTTFS contribution from the logic solver for each SIF and for the entire unit. Again, this would be very complicated to do by hand because it's different for each unit. Luckily, exSILentia will do that for you. So in this case, now that all 3 SIFs are modeled, I simply select Unit MTTFS from the silver menu, and it spits out the MTTFS for each unit. In this case, for the furnace, the MTTFS is 65.86 years. This is so easy to do in exSILentia, and obviously my sample problem is pretty sparse. I only have 2 units, but if you have a normal system, my guess is that you're going to have a lot of different units, and you can have the MTTFS listed right there for each unit. So it calculates it per SIF, per part of the SIF, and per unit. So let's summarize what we've gone over. Minimizing the number of spurious trips in a system is a top priority for many due to the high cost of loss of production. You don't want your plant to trip for no reason. Obviously, in the event of a hazard scenario, it's a must. But when you're running fine and there are no hazards happening, you don't want your plant to trip. Uptime is of the utmost importance to the people running that plant. And so we know now that the spurious trip rate can be minimized by using redundant architectures such as the 2 out of 2 and 2 out of 3 configurations. But exSILentia will automatically calculate the MTTFS for SIFs units, allowing users to optimize their safety system to avoid false trips. Again, it's so easy to select something different as far as equipment goes, as far as your SIF architecture goes, and see how that affects your MTTFS. You definitely want to maximize that number to minimize the spurious trips in your system and have a smooth running plant. If you want to know more, we do have a few exida Academy courses coming up. We're teaching process hazard analysis with FACS, layer of protection analysis with LOPA, safety requirement specification with the SRS tool, and SIL verification with Silver. All of these are happening the week of September 11th in Houston. I will be there, and I hope that you'll join us to learn about how you can use exSILentia to keep your system safe. If you want to know more, you can find exida on Twitter. We have our website, exida.com. We are on LinkedIn. We are on Facebook. And if you have a suggestion for a webinar topic, we'd love for you to tell us. You can take that to academy@exida.com. And we want these webinars to be of value to you. We love doing them, but we want you to learn something from them. So if you have something you want to know, please let us know. And that's it for today. I don't see any questions yet, so what I'm going to do is if you have any questions, please email me. My email is khildenbrandt@exida.com, and we will compile all the questions. We'll send them out to all of you so you can benefit from what people are learning from this webinar. Thank you again for joining us. I hope you have a great day and take care.